Hello everyone, we are looking at question 28. The question says that a voltmeter reads 5 volt at full scale deflection and is graded as 2000 ohms per volt. The question is what resistance should be connected in series with it so that it reads 12 volt at full scale deflection. The options given to us are 2.8 into 10 raised to 4 ohms, 3.6 into 10 raised to 4 ohms, 1.4 into 10 raised to 4 ohms, and lastly 7.2 into 10 raised to 4 ohms, and the correct answer to this question is option C, that is 1.4 into 10 raised to 4 ohms. Now let's take a look at how we can solve this sum. Now to do that, we must recall what exactly is a voltmeter. So if we try to look inside a voltmeter, we should recall that a voltmeter on the inside is nothing but a galvanometer connected with a high series resistance. So let us just quickly revise what a voltmeter comprises of. Now this moving coil galvanometer we know is a very delicate instrument, and it is so delicate that even a few orders of milliamp current can cause it to go into full scale deflection. So even if you measure a small potential difference, there will be full scale deflection. And exactly for this reason, what we do is we must convert this galvanometer into a voltmeter by adding a high resistance to this instrument. So if I want to measure large potential difference, the effective resistance of the instrument should be high, and this is achieved by connecting a high value resistor in series with the moving coil galvanometer. So as you can see, I have connected a high value resistor which I will call as RS in series with the galvanometer, and this is how I construct my voltmeter. Now an ideal voltmeter has an infinite resistance, and it does so that when it is connected into a circuit, it should not change the value of current. So this was a quick recap about what happens inside a voltmeter. Now once you have done that, let me say that let us assume that the current flowing through the circuit is given the symbol I subscript G. So Ig is the current flowing in the circuit for which there is full scale deflection. Now I say that let me assume that the resistance of the galvanometer is given the symbol G, and this high value resistor has the symbol RS. So if I ask you what is the total resistance inside a voltmeter, you can say very quickly that the total resistance inside the voltmeter would be the resistance of this galvanometer plus this resistance value, that is the resistance of this high value resistor which I have connected in series. So if I have to write down the total resistance of the circuit, it would be capital G plus RS. Now the reason I am revising this with you is to tell you that already inside a voltmeter there is this high value resistance RS, as you can see. So total resistance of any voltmeter is the sum of the resistance of the galvanometer which is inside plus the value of the resistance which you have connected in series. Now it's very straightforward. If this is the total resistance, I just have to apply Ohm's law and I get an equation for the voltmeter, that is V, which is the potential difference, is equal to Ig into G plus Rs, where G plus Rs is the total resistance that we just spoke about. Once I have this equation for the galvanometer, I'm going to save it, and then I'm going to look at what this sum is asking me to do. Now in this sum, they are saying that the full scale deflection happens when we have potential difference of 5 volt. Now we have also been told that the grade of the voltmeter is 2000 ohm per volt. So you can see that the grading is written on the voltmeter, it's 2000 ohms per volt. So as the voltmeter has full scale deflection at 5 volt, and because it is graded as 2000 ohm per volt, it's very simple to find out what is the resistance of this voltmeter. It's very simple. The grading is 2000 ohms per volt and full scale deflection is happening at 5 volts. So there is 2000 ohm resistance for each volt, and because there is a full scale deflection at 5 volt, the total resistance, that is G plus Rs, will be 5 into 2000, that is 10,000 ohms. Now this is exactly why I revised what is inside a voltmeter, to let you know that when you calculate the resistance from the grade, that is you got 10,000 ohms as the resistance, what resistance are you actually calculating? You are calculating the total resistance of the voltmeter, which already includes the resistance of the galvanometer and the resistance of the resistor in series. So what you got, this value 10,000 ohms, is nothing but G plus Rs. So we have been given that the total resistance of the voltmeter when the full scale deflection happens at 5 volt is 10,000 ohms. I'm going to need all this data, so I'm going to save it on my board. And now I can continue to solve the sum in a very simple way. I have got what I wanted. I know that the total resistance is 10,000 ohms and I know that this happens for 5 volt. So now I can find the full scale deflection current. And if I want current, then I can rearrange this formula. What I do is I look at this formula, that is V is equal to Ig into G plus Rs, and I rearrange it. I take Ig down to one side and then I take V in the numerator on the other side. And finally, I divide this by G plus Rs, which becomes the denominator. And here is my formula for the full scale deflection current. Now look here how quickly we can find the current. We know that V is 5. So for V, I'm going to write 5 volt. And we just found that the total resistance G plus Rs is 10,000 ohms. So I'm going to write 10,000 ohms below. And this gives me the full scale deflection current Ig, which is 1 upon 2000 ampere. I'm going to need this data. So I save it as equation 1. Now let's see what the question says. Now the question is asked, what happens if I want full scale deflection at 12 volt? Well, even if you want full scale deflection at 12 volt, it doesn't change which current is going to cause full scale deflection. The galvanometer inside is the same and therefore the full scale deflection current remains the same. So I need this data, that is Ig is 1 upon 2000 ampere, which is why I'm going to save it. But now I look at the second case that now I want V is equal to 12 volt, but Ig still remains 1 upon 2000 A. So I can still use the same formula, and this formula now I'm going to rearrange in a different way, where I'm going to write total resistance G plus Rs is equal to V upon Ig. Now using this new form of the formula, I can find what would be the new total resistance in such a circuit, because now the voltage should be 12 volts, but the full scale deflection current is the same, and therefore I'm going to bring 1 upon 2000 ampere down. This gives me the new total resistance, that is 24,000 ohms. So what have we found so far? Initially, when the full scale deflection was happening at 5 volt, the total resistance of the circuit was 10,000 ohms. Now when the full scale deflection is happening at 12 volt, the total resistance is 24,000 ohms, and this is what we are going to need. So I'm going to save it on my board, and now it's pretty straightforward. The question says, how much more additional resistance will be connected? That is, what value of resistance should I connect to this voltmeter to get the new resistance? So you can see initially I had only 10,000. Now I need 24,000. So how much should I connect? The resistance that I should connect would be the new resistance minus the old resistance. Already 10,000 ohms was in the circuit. Now I want 24,000 ohms. So what I should connect is 14,000 ohm resistor, which I can write as 1.4 into 10 raised to 4 ohms, and that solves my sum. That is, the resistance in series that must be connected to this circuit for full scale deflection at 12 volt is 1.4 into 10 raised to 4 ohms. Usually people make a mistake that they write the answer as 24,000 ohms. They have not asked you what is the new resistance required. They have asked you how much should I connect. So you must realize that already 10,000 ohms was present in the circuit. Now what you need is 24,000 ohms. So what you must connect is a resistor of 14,000 ohm value. So I hope you understood this video, and thank you for watching.